Good morning, everyone. It's Friday, 3-27, and we're going to start GEO 319 Friday lab/lecture. So, yeah, normal rules apply. Please ask questions if you want. Just talk. The chat thing's really awkward for me because I have to pay attention to the chat window. So if you have a question, please just talk. So today what we're going to do is we're going to do a lab activity. I'm going to lecture a little bit here on some statistical interpretation methods. But the basic idea is to look at some isotope data and play around with some interpretation of this isotope data. Okay, so to do that, we're going to talk a bit about hypothesis testing and testing the difference between data populations. So I'm going to start sharing my screen here. And you should be seeing my screen, and we'll start talking about populations and testing populations. Before we get started here on the lecture, all the files that you need for this lab are up on Moodle under Lab 8, Isotope Biogeochemistry. There's a folder. It's going to have 2 Excel files which have the data in them, one with carbon isotope data, one with nitrogen isotope data. It has a Word file, which is basically the assignment or the lab. And then it has a couple papers that this data is, that will help interpretation with the data or that the data is based on. So download all those files and we'll, as we go along here, that's what we'll use to do the lab. Okay, so the basic idea here is that we're going to look at a few different populations or samples of different plant species or biological species and look at their isotope compositions and compare them. And so one of the big things that we need to do when we have, say we've got in your carbon isotope data today, you're going to be comparing plants during a normal water year and during a drought water year, and you're going to be trying to decide whether there is an isotope difference between wet years or dry years. And this is a really common problem in scientific literature, is trying to decide whether your data is different between one population that has a given treatment and another population that has another treatment. All right, so this problem is essentially trying to test whether your datas are coming from a single population or from 2 different populations. So what do I mean by a population? Well, we can think of any set of data as coming from a statistical distribution. All right, and so the classic thing that we think of when we talk about a statistical distribution is a bell-shaped curve. All right, so as an example, here we have a population, all right, and we would expect, this is the probability or the number of the samples that fall on some value in that population. So for us here today, this might be delta 13C. All right, and this is the the probability that we would expect for a given value of delta 13C. So this is what we call the maximum likelihood value, right? This would be the value that we would most likely see most often. And this, if it's a normal distribution, is equal to the mean or the average. All right, and I'm going to call the mean, we generally call that mu. All right, for a population. All right, so the mean, if I've got a normally distributed population, all right, that's this bell curve. The mean would be the most likely number I would get. So let's say I drew 100, I had 100 trees that I sampled carbon 13 from. The mean value would be the value that I would expect to see, have the highest probability of seeing. Okay, so then what we're trying to do when we compare two populations is we are comparing the means of those populations. All right, so when we compare two populations, we compare the mean and we try to decide whether the means are coming from the same population or whether they're coming from different populations. And so this process we often do with a test called the student's t-test. So we test whether populations have the same mean. All right, and so your first question might be, well, why can't I just look and see if the means are different or not? All right, I calculate the average for this population, I calculate the average for this population, and if they're different, they're different. Well, the thing is that we don't know exactly what the true mean of that population is. All right, we get a sample, we get some finite number of points out of this bell curve, and we calculate the mean from that, but we don't know whether that's the true mean of the population or not. So the trick here is to compare the difference of the means to the uncertainty of the mean. So we compare, we're basically comparing the difference of the means to the uncertainty of the mean. Uncertainty. All right, and this process, very commonly, we can do it. There's a whole, variety of ways that people do this, but the most common way people do this is with what's called the t-test, student's t-test. And essentially, student's t-test just calculates basically this. It compares the difference between the means to the uncertainty of the means, and it tells us the probability that those means came from the same population, or the probability that they came from different populations. So we do this, we often quote this p-value, all right? And the p-value is the probability that we would, the p-values are really, I always get tied up trying to think about it. It is the probability that we would mistakenly think that these things are the same or come from different populations. So the probability that we would falsely think that these things are different. All right, so as an example, this shows two populations. Say this here, you're going to make bar graphs just like this. And this is here, this is delta C13 for a drought year. And this is delta C13 for a dry year. All right. And this number right here, this is the mean. And these error bars are given by the uncertainty or the standard deviation, which is the spread of this curve around the mean. So we'll call this the standard deviation. All right, so these are given by the standard deviation mu. All right, so this error bar is basically some indication of the error of our mean or the uncertainty of our mean. This is a terrible mean. I'm going to erase it and rewrite it. Okay, so this value here is mu. This value here is sort of an idea of the uncertainty of mu. All right, and you can see that these error bars overlap the mean in each case, right? So it makes intuitive sense that we would think, hey, I don't think I can tell the difference between these two values. And so the probability of me falsely thinking that I am going to call these different populations is high. It's greater than 5% here. If we run the t-test here, we would probably say that there's probably a 99% probability that we would falsely say these are coming from different populations, or a 1% probability that they come from the same or from different populations. Sorry, a 99% probability that they come from the same population. All right, here we have another data set. All right, say this is delta C13 of the dry year. This is delta C13 of the wet year. Again, these are the two means. These bars are my uncertainty on the mean. And you can see I have a very big difference between these two population means. All right, and it's much greater than the uncertainty of that mean. So here, I have a really low probability of falsely thinking they come from the same population. So it's less than a 5% chance that it's less than a 5% chance that these are actually coming from the same population. They're probably, with 95% confidence or greater, coming from different populations. All right, so that's the nuts and bolts of the t-test. We're comparing two population averages. We compare the difference between those averages to the uncertainty, how well we know that average, and we decide whether they're coming from the same population or different populations. All right.
Hey, now I have a question.
Yeah.
Wait, can you explain again the p-value thing with the first bar graph? Like, so it's a 99% chance that they are from different populations or from the same population?
Okay, so here, let's say they're saying, okay, this good question. The p-value, I always have to stop and think about it. It's non-intuitive.
Yeah.
Okay, so the p-value right here they're saying is greater than 0.05. or this would be 5%, right? If I multiplied this by 100, I'd get 5%.
Yeah.
All right. So this is saying that there is greater, there is greater than a 5% chance that we would,
Doesn't it have to do with the null hypothesis, Professor?
It does.
well, that's exactly what I'm trying to say. The null hypothesis is that these are from the same population.
So,
Right.
okay, sir.
The null hypothesis says these are from the same population.
Right.
So the probability, the P factor here is the probability that I falsely reject the null hypothesis. That means, in layman's terms, that says this is the probability that these are actually the same population, but I think they're different.
Okay. So it's a 5% chance that they are from the same population?
A 5% chance that they are from different populations.
Oh, okay.
Well, sir.
Yeah, Mark.
Yeah. In order to do that, you need your null hypothesis, which you stated. The null hypothesis being that they're from the same population, right?
The null hypothesis is that there is no difference between the populations.
Right. So then the P would be the probability that it would be from different populations, given that the null hypothesis is true.
The P value, Mark, is
It's the
this. It is the
probability.
probability that you falsely reject the null hypothesis. That is the
Right.
definition of the P value. What that means is it's essentially the probability that these are not from the same population.
I have a question. Is
Yeah.
there, we have to find the p-value itself?
You're going to, so when you do a t-test, you're going to do the t-test. And what the t-test actually gives you is the probability that these things are different. So it is, if you want to figure out the p-value from the t-test value, you got to go, so p-value, so you're going to get, when you do the t-test, we'll do the t-test in lab today. When you get the t-test, the p-value is equal to 1 minus what you get for the t-test. All right. So the t-test gives you the probability that they're from different populations. All right. So the p-value is 1 minus the t-test. That's the probability that that you would falsely think that they are from the.
So is the t-test the only way that you can come about P?
So hypothesis testing is like a whole statistical
Okay.
Right.
area of study. The t-test is the most common way we do it. It makes a few assumptions. It makes the assumption that that things are normally distributed and standardly, they have a standard distribution, but it's by far the most common way we do it. And the reason why, there's a lot of reasons, theoretical reasons why we do it that way. I don't want to get into all those. The bottom line is that the uncertainty of the mean, how well we think we know the mean, will follow this student's distribution if things are normally distributed. And it's just a really convenient way to compare the difference of two population means to how uncertain we are on those means. All right, so P greater than 5% says, so this P of 0.05 all right, is really common. So this is by far in natural sciences, this is our cutoff value. So anytime P is greater than 0.05, we say these are probably the same population. It isn't until P is less than 0.05. So there's less than a 5% chance that these are coming from the same population. This is our cutoff for saying they're actually different. So these two are different. If P is greater than 0.05, this is the probability that they are not different. All right. If it's greater than 5%, I'm sorry, this is the probability that they are the same population. If it's greater than 95%, we say they're the same population. All right, all right, any more questions on the p-value? The bottom line is this is the probability that you falsely think that they come from different populations. All right. Okay, so we're going to look at some data, all right? And this is, in fact, a screenshot of the data you're going to look at today, all right? So here we've got plant tissue samples, and some of them are taken during a normal precipitation year. So this is the population. This is species A. So we're going to look at a paper today where they look at ponderosa pine and they look at, for example, they look at ponderosa pine, say in Montana, and ponderosa pine in North Dakota. All right, so that might be species A and species B. And they look, so this set of data is all the samples they took during a normal year from this species, species A. And then they went over and they took plant tissue samples during a drought year. All right, so our job here is to compare these two populations and decide whether they're the same or different. All right, so to do that, we're going to calculate the mean, all right, of each of these populations. We're going to calculate the standard deviation, all right, of each of these populations. So if we go back to our bell curve, all right, we're going to calculate the mean. And then we're going to calculate the standard deviation, which is this value here. Sigma. Oh, that's not a sigma, that's a 6. That's a derivative. Dyslexic this morning. All right, we're going to calculate sigma, which is just a measure of how spread out this curve is, and essentially gives me an idea of how uncertain I am in my mean. All right. Okay, so we're going to calculate mu here. We're going to calculate sigma here. I'm going to show you how to do that in Excel. And then we're going to calculate the value of the t-test here. All right, we're going to do that for species A and again for species B. And then we're going to answer some questions. We're going to make a bar chart like the one we looked at previously. we're going to make a bar chart kind of like this. So we'd have species A here, drought, wet year. We'd have some error bars, and we can kind of compare the means and the error or the standard deviation between these two. And you do that for species A and then for species B.
Hey, sir, did you cover degrees of freedom?
Nope, we're not going that deep.
Okay.
All right. So this is a chart or an example of what our bar charts should look like. All right. They're going to have some isotope values. They're going to have error bars, and we're going to be able to compare the mean. So this would be the mean. So this value here would be the mean of species A during a normal year. And this is going to be mu sub B during the dry year. All right, and then we're going to have these error bars from our standard deviation. So this is sigma B dry. And essentially what the t-test is doing is comparing, very roughly comparing the difference between these two means and taking into account this sigma. And what Mark is referring to, degrees of freedom, well, basically the larger the number of samples I have, the better I know what the mean is. So the smaller this error bar gets, and the better I know the difference between these two populations. But we're not going to get into the heavy details. Okay. So we're gonna get started. So I've got here I'll delete this guy. So when you download your sheet, you're going to end up with, you're going to get something like this. All right, so you got species A here, all the tree samples, plant tissues for the normal year and the dry year, right? Here's species B, normal year, dry year. So the first thing we need to do is go in and calculate the means and the standard deviations. So I'll show you the Excel formula to do this, and then you guys will run with it. If you have questions, so I'll show you all this. Then I think what we can do is, if you guys have questions, like something's not working, I think you can share your screen with me, and then I can help you answer or figure out what we need to do. Or you can just ask me and I'll try and do it online so everyone can see it. Okay, so the mean in Excel is a function. So anytime you want to do a function in a cell in Excel, I don't know how many people have used Excel a lot. The first thing you got to do is type in equals. That tells Excel you're going to make a calculation. Then the mean is average. This is a great example of why Excel isn't really written by scientists. Average and mean are not synonymous, but at any rate, average. Okay, and then you got to tell it the range of numbers to take the average over. So it's average, then a parentheses, right? And then I'm going to tell it take the average of all of these 10 samples. All right. Then I'm going to close the parentheses. Hit enter. Okay, so, and I'm going to label these. So here's the mean. All right, negative 29.31. The standard deviation. All right, the formula equals STDEV all the numbers, hit enter. Okay, so my mean is negative 29.31. My standard deviation is 1.1. All right, and then you gotta calculate those for all the different tree species. And then you get the joy of trying to figure out how to use Excel's chart making capabilities. So as an example, I'll just do one for species A. I would highlight my data, insert, insert chart, 2D column, and I get these columns. Error bars are this whole thing. It's like an odyssey trying to figure out error bars. Good luck. But you go to add chart element, error bars, and then we need to do custom error bars. So we could add a fixed value, we could add a percentage, but we want to specify the value. All right. Then somehow my error bars don't even show up. But at any rate, that's how you put the error bars in. Then you just got to wrestle with Excel and figure out how to get them to show up. I'm not sure why these are not plotting on this other side, but that's part of Excel. Okay, I will be here listening. If you have questions, please ask, and then I'll try and answer them for everybody. Or if we need to figure out how to just have you share your screen with me, we can do that. Any questions?
So right now we're making a bar graph of the mean, or the mean and the standard deviation.
It's the mean. So this bar graph is just the mean. This value here is negative 29.31. And this value here is negative 25.67. So each bar is one of the means. One is the mean during the normal year. This is the mean during the dry year. And what the standard deviation is giving me these error bars here.
Oh, okay.
Does that make sense?
Yeah, it does.
Okay.
Why is the error bar only going up instead of extending
Excel,
further down?
Elliot, it's some Excel thing that I have to, I don't know. Hopefully it'll, I mean, it's something's happening here where it's not plotting. It should, this says both.
Oh, okay, yeah.
I don't know, minus, plus. It's not doing a darn thing different when I check all these different options. plus. So it's some Excel thing, but you should be able to plot them in both directions. It's just a matter of figuring out how to
Okay.
tell Excel how to do it. I try to use Excel as little as possible, but so I got to figure it out. But you guys can do it. I have faith in you.
Okay.
There's no reason why this shouldn't be plotting on both.
There it goes.
Peyton,
Yeah.
for the positive error value, what did you use again?
So it should go up. So it should go plus 1.1 and it should go down negative 1.1. So for the
Okay.
negative, I just multiplied these by -1.
Okay.
Does that make sense? So this is the standard deviation. This is just the absolute value up and down it should go.
Mhm.
Oh, I think I understand what it's doing. Hang on. So these values, I think, should be, let me try this, equals that plus that equals this minus this. Let's try this.
Hey, Professor. Should our chart include species B too, or just species A?
Yeah, it definitely should have species B.
Okay.
There's so download the paper Zhang 1997, and it has an example of what exactly we want this. So positive error value. Negative error value. Let's see what this does. No, that's not doing it right. Ugh. Bada boom.
Are we putting species A and species B in the same chart or the different charts?
They should be in the same chart. But it doesn't matter. If you can't figure out how to put them in the same chart, they can be in different charts. You can put them in the same chart. There's absolutely no reason I see why this will not plot both directions, but it's not plotting both directions. So,
Peyton,
yeah.
for turning into last week's lab, I took a bunch of pictures of my paper copy, and I can only upload one file, I think, on the Moodle drop.
Okay.
Can I email you all those pictures, or should I try to make it into one file?
You can make it into one file. You're on a Mac, right, Wendell?
Yeah.
So in preview, if you when you open up one of these in preview, you can drag all the other ones into that same file in preview,
Okay.
and it should stitch them into one file.
Okay, I'll figure it out.
I can show you how to do that if you want to even try office hours sometime.
Okay.
All right, if anybody else can figure out how to make these things, there's zero reason I can figure out why this thing is not working.
Is that number, the 1.1, supposed to extend 1.1 up and 1.1 down, or should it be like 0.55 up and 0.55 down?
Now it should be 1.1 up and 1.1 down.
Can you just put 2 on, 1 negative and 1 positive?
That's what I did.
Oh, dang.
So I'm telling it go 1.1 up and go negative 1.1 down. And it's not working. Let me try. This. There we
So
go.
what if you were to do standard error?
Oh, standard error, it won't, it's calculating the standard error of these two numbers, so it's not really right. I just figured it out. So here's how you do it. You go to custom value. It's probably different whether you're on a Mac or whether you're on a PC and what year of Excel you have. But what I did is custom specify value, and for positive error value and for negative error value, I used the same thing. I just used the standard deviation. And then it's giving me bars both ways.
Okay.
And if you want them both on the same, if you want them both on the same, first of all, chart, you can just, if I go here and I chart design, select data, I can add another series. All right, and Y values are this guy. This would be species B.
Professor, are you going to show us how to do a t-test in Excel?
Oh yeah, t-test. Let's do it. Okay. Chart is getting close already. Now for the t-test. So t-test, the function is equals t dot test. All right. Now you got to give it the first population. So array 1 is the first population. All right. Array 2 is the second population. All right. Now, tails is 2. It basically just is whether you want to compare the means only, you think one population has to be greater than the other, then you would use a one-side t-test. But don't worry about it. Tails are 2. All right. And the type means whether you want to pool them together to get the variance or treat their variances separate. Doesn't matter. We're going to do one. We're going to pool the variance. All right. So first array, second array, tails, a two-tailed test, and we're going to pool the variance with 1. All right. Close the brackets. Okay. So this value is the probability that these are different species. All right. So if I wanted that in percentage, I could go like this, equals. So this is my, so my p-value, let's do this first. P-value, the probability that they are 1, let's see, wait, this might be the p-value. This is the probability that these are.
No, isn't that your t value?
Yeah, this is my t-value. So my p-value.
1 minus.
No, this is my p-value. Yeah, 1 minus. So the probability that these are the same population is 99.99%. The probability that they are different populations is 0.001. All right, and this, so if you look at these means look the same. These standard deviations look, you know, they look like the same thing, and within the error, they're definitely the same. So I could do this for this guy, t equals t dot test. This array, two tails.
We don't include the means.
You included the mean, sir.
Yeah, we don't want to include the means, right?
Yeah.
Right.
So the probability that these are different populations is 0.83. And the probability that they are the same population is 0.16. So this is the probability that these are the.
So I have a question. When you say population, like what does that exactly mean in this context?
A population has a very, okay. These are actually samples. A population is, if we go back, let's do this really quick. So we go back, this is a bell curve, right? This curve is this fictitious thing. And this is a population.
The curve.
The curve. And it says that there's
the
this
sample
magical
would be
statistical
anything underneath
distribution
the
that's
curve?
continuous that my sample comes from. So a sample, this would be a sample, all right? And a sample is basically, so let's say this is on this x-axis, this is delta 13C. All right. So this is my population. What I have is a sample, which is a random drawing of these guys. So maybe I've got a value here, I've got a value here, I've got a value here, I got a value here, I got a value here. So this is like a random draw out of this population. And what you're hoping, let's say I got a value here, I got a value here. Okay, so this is my population mean. And my sample mean is whatever I got out of my sample. So so these guys over here, these are a sample from this population. And those are statistical definitions. When we get a set of data, we're saying that's a subset that comes from this greater population, that if we had all the samples in the world, if we were able to measure all of them, they would follow this population. Does that make sense? It's kind of an abstract idea.
Yeah.
But this we call the population mean, this we call the sample mean, and essentially, if we knew the population mean, we wouldn't have to do this t-test. But we never know the population mean, we only know the sample mean. Okay, so these guys have the probability that these are different populations is, less than 0.01%. And the probability that these are different populations is 84%. All right, the probability that these are the same populations is 16%. The probability that these are the same populations is 99%. So probability different, not probability. And to get this value, I just did 1 minus this value. Okay. You're going to do this for both carbon and some nitrogen. Oh, we're already out of time. Jeez, time flies. Any other questions while we're on?
Due next Friday. This is due next Friday. Cool.
All right, any other class questions for me right now?
When do you want me to do that snow plot that you just sent over my way this morning?
Did you get the
I got the data.
do you have all the other like the blank sheet to make the snow plot on and the information on?
You gave me the example sheet.
Do you have a clean one like the example sheet, and do you have the key?
Let me check really quick.
tell you what, I'll just post it all on Moodle.
Okay. Sounds
Um,
good.
Yeah, I haven't graded. Can't remember if I've graded them or not. But whenever you can get it in, Pat.
Okay. Thank you.
All right, I will. If no one, anyone else have questions?
No.
Okay. Feel free to email me any questions, and we'll talk to you guys soon. Have a good weekend.